Designing a 90nm CMOS OR gate using artificial neural networks, ANS. Abstract. Over the last few decades, this paper describes a method for simplifying electronic circuits by employing complementary metal oxide semiconductors, CMOS, transistors and mapping them to similar artificial neural networks, ANS. The implementation of such circuits in AN results in software implementation of complicated circuits, which is less expensive than their hardware equivalent. In this research, a multiple-layer AN for the OR gate is utilized to control a previously constructed 90nm CMOS OR gate. Simple artificial neurons replace the transistors used in CMOS. The weights in this AN are fixed, and negative weights are taken into account for the inverters. Keywords: Complementary Metal Oxide Semiconductors, CMOS, Artificial Neural Networks, ANS, OR gate. Introduction. In the recent 40 years, Moore's law has been rapidly increasing VLSI arrangement through CMOS improvement scaling over the last 40 years. Typically, the number of semiconductors in integrated circuits doubles after 18 to 2 years. This type of advanced scaling has worked well in the semiconductor sector, but in recent years, the speed of this scaling has slowed. Intelligent computing is becoming more prevalent in modern computing. Artificial neural networks, ANS, are the greatest way to introduce intelligence into computers. 1. Research is being conducted to construct models that may be utilized in a wide range of applications such as medical informatics, handwriting recognition, speech recognition, and other pattern recognition applications. 3. By keeping the hardware basic, the creation of these models leads to the construction of more than 67 complicated circuits in software. These factors reduce the cost of these circuits. If ANS are built in a way that is analogous to CMOS circuits, mapping ANS to hardware circuits using CMOS becomes straightforward. 5. First Cell M has contributed to the field of hardware implementation of artificial neural networks. 1. Some work has previously been done in this sector, including CMOS circuits that receive synaptic inputs and create a pulse width modulated output waveform of constant frequency based on activation level 2. Based on supervised learning, logic gates were constructed in a single layer and a two-layer feed-forward neural network. 3. Another technique employed artificial neural network, AN, to illustrate the manner in which the biological system was processed in the analog domain by employing analog components such as a Gilbert cell multiplier, an adder, and a neuron activation function for implementation. 4. Hui et al. Worked on the use of artificial neural networks on segmented arc Heather failure prediction. 5. Two-cell design. The CMOS OR gate is divided into two parts. The CMOS gate's top part is made up of two series-connected transistors. In the top section, PMOS is employed. It is sometimes referred to as a pull-up, pun. A and B are the transistor's inputs, which are reversed before being linked to the transistor. The value of VDD is always 1. The CMOS gate's bottom part is made up of two parallel connected transistors. In the lower part, NMOS is employed. It is sometimes referred to as pull-down, PDN. The transistor inputs are A and B. The value of VSS is always 0. When A and B are both 0, the upper transistors in the series get inputs of 1. In the case of lower transistors, the 0 input in both parallel transistors prevent VSS from being used. When A equals 0 and B equals 1, the first higher transistor receives a 1 as input, while the second upper transistor receives a 0 as input and blocks the path for VDD. The first lower transistor receives a 0 and so blocks the path for VSS. The second lower transistor outputs 1 and makes room for VSS. The result will be VSS in this case. Similarly, as indicated in Fig. 1.3.5, the additional outputs received are the outputs of an OR gate. 3. Proposed work. In the case of an analogous AND circuit, the OR gate already created using transistors and inverters is designed using a multiple-layer artificial neural network, AN. Simple artificial neurons take the role of transistors. Negative weights are put on the links to replace the inverters. The AN circuit is implemented using many layers of neurons. 5. OR gate. Fig. 2.1 CMOS OR gate using multiple layer AN. Figure 2.1 depicts a multiple layer AN, with T1 and T2 representing artificial neurons that represent two transistors linked in series. T3 and T4 are neurons that depict parallel connected transistors. N1 and N2 are two straightforward neurons. A basic perceptron is one neuron, and a referee neuron is another. T1s weighted, W1 and W2, inputs are VDD and X1, with Y1 as the output. T2s weighted, W7 and W8, inputs are Y1 and X2, and its output is Y2. T3s weighted, W3 and W4, inputs are X1 and VSS, with Y3 as the output. T4S weighted, W5 and W6, inputs and output are VSS and X2, respectively 5. These ANDs are based on fundamental self-organizing maps, SOMs, which use unsupervised learning. As a result, the synaptic weights are fixed in this location. When using inverted transistors, the weights are negative. Other weights are held constant at a positive value. As noted in the 75 introductions, work on this topic has already been done, however the work in this article is a method to creating extremely basic circuits. Simple circuits are easy to construct. This technology might be used in the future to simplify complex circuits for a number of applications. Fig. 2.2.1 CMOS OR gate test bench. Only OR gate is covered here since the logic underlying OR operation gates is mapped with CMOS OR gate, which is then mapped to a basic AN. However, any sort of logic circuit may be mapped using AN. The concepts of VDD and VSS are discussed in detail here. As in CMOS OR gate, VDD is always binary 1 and VSS is always binary 0. With negative weight, the inverter function may be simply accomplished. Furthermore, focus is placed on mapping AN circuits to replace complex electrical hardware circuits with AN models that may be implemented in software. Examples that calculate the inputs and outputs of the CMOS OR gate using AN. For results references. Various inputs to various artificial neurons utilized in the CMOS OR AN, as well as the corresponding output A and B are the OR gate's inputs, while Y is the binary output. However, the AN works with bipolar inputs and outputs. Conclusion: this study takes the method of designing simple circuits to construct fundamental logic gates using CMOS. CMOS circuits are presently employed in a wide range of products. ANDs are also getting increasingly popular these days. With the growth of this technology, this technique will lead to the construction of basic AN circuits, as well as the hardware implementation of the AN models.